All right.
Yes.
All right. So, all right. A little annoying here. Why this is right in the middle of the screen, I don't know. All right. So it's just describing the setup here, and so we have a magnetic field that points into the page. It's based on the drawing. The crosses mean into the page, and the rails are separated by 0.5 meter. And the question is, what is the current through the light bulb in this situation? And of course, what's going on is that the area is changing in the presence of this magnetic field. So the flux is a time-dependent quantity here, magnetic flux. And so we invoke Faraday's law, as shown here on the right, and replacing that explicitly with the definition of the flux, being that the flux is perpendicular. Well, being that the magnetic field is perpendicular, or at least aligned, I'm sure say it's parallel with the area between the rails, and so it's really not a dot product to contend with. And also the magnetic field constant, and so the only thing that's varying here is the area. And also, of course, the separation, we're keeping that constant. So really the only thing is changing is the distance between the rail, the distance between the rod and the light bulb as it moves over to the right. It's pointing by the arrow here. So we have this relationship between the EMF and the how fast or the rate change of the position for the rod with respect to the light bulb. Okay. So we have this relationship here. It's plugged in the values, and from that, we can determine explicitly what the EMF. Of course, it's not the EMF that we're really directly after. We need it, but it's just the current. So this turns out to be minus 5 volts, based on the parameters that are given to us. Just a check here. Can you guys still hear me?
Yes. Yes.
Okay. All right. So now, in order to determine the current, we need to use Ohm's law. Being that the resistance is given to us, 1.5 ohms. This is the resistance of the light bulb. We assume that the rail and the rod has insignificant resistance, at least compared to that to the light bulb. And so we have the voltage, and so now we can calculate the current directly, which turns out to be 3.3 amps in this case. More than enough to light a light bulb such as one here, I would guess. So the next part of this is how much power then is delivered to the light bulb based on moving the rod over to the right at 10 meters per second. So we know power is equal to voltage times current. That's what we have here. And so we have these quantities. We have the voltage. We have the current. And so it turns out to be about 16.5 watts. Next question, the next part of this question is, how much force then is required to move this rod at this speed? It's more of a 207 type problem. We have the power, and we have the velocity. Remember, it's force through a velocity. Force through a distance is energy. Velocity, it gives you power, the time rate change of energy. And so we have this relationship. We know what the velocity is. We now know what the power is, so we can determine the force needed to move the rod. And that turns out to be 1.65 newtons. Actually, not quite not a lot. Easily, it's probably a simple conversion to pounds to newtons is a factor of 4 roughly. So you divide this by 4, and that would roughly, what is the amount of force per pound. So it's not a lot, but still requires something. Okay. Move on to the next problem. So we have this circuit that's shown here. I don't know if you can see my mouse moving around. This wire is bent into two circular arcs, different radii. One's at 4 meters, the other at 5. And the angle of the arc is 90 degrees, pi over 2. And what we're asked is to calculate the magnetic field, the magnitude and direction at point 0 here, or point O, our observation point. Okay, so the current is given to us, radius is, have the geometry you need to use Béal-Savart. And I don't know if I can move this, something's right in the middle of the screen. I can't seem to get rid of it, but so be it. So, our path, we basically take this section as the current, which is in the bottom part is to the left and the top part is to the right. And from A to B is radially away from our observation point, and then from the case for C to D is also radially, but toward O. But these currents do not contribute to the magnetic field because they're parallel to the DS and the R. It's basically the vector tells us this direction of the current. Well, I mean, this is position of the current with respect to our observation point. And DS cross R, of course, is 0 in that given situation. So the contributions of the segment current going from A to B and C to D, they do not contribute to magnetic field. So that can be ignored here. Right? But every point on the circular curve D to A, the vectors DS and R are perpendicular to each other everywhere on here, everywhere on this point. But there's some niceties about this. The circular, at least that, in our point O is the center of the circle. Okay, and so now we're looking at the segment here from point D to A, the circular segment. Of course, we know already that that angle between R and DS must be perpendicular on a circular arc if we're observing this from the center of the arc or of the circle. And so consequently, it's always 90 degrees. Sine of 90 is always 1. And so to really deal with the cross product anywhere, does it change? And by the way, the magnitude of the unit vector R is 1, so that's why it disappeared. And so we're just left with this relationship in terms of this, for every segment of DS, a small segment of DS, that's the contribution to the magnetic field dB at the observation point O. So what we want to do, though, we want to integrate from 0 to theta. In this case, we know theta in this case is pi over 2. We don't really have the integral differential part in the units, or at least in version that we would like, the relationship between theta. But we know that ds is equal to r, in this case, r sub 1 times d theta. Consequently, we can rewrite this in the following way. Of course, all I've done here in this next step is just pulled out the constants, which are independent. As we, independent does not change as we pass through this this arc. And what I've done here is I substituted in ds for r d theta. And r is constant across this arc. So that too can be pulled out. And so we're just left with this relationship here. Okay, put in the values that were given to us. 10 amps is the current. The distance, R1 is 4 meters, and our arc, that is pi over 2. That turns out to be nearly 4 times 10 to the minus 7 Tesla, 3.93 times 10 to the minus 7. But we're not done yet. We've only determined the contribution from this, this bottom segment. We now have to do the top segment. But before going into that, we're asked not only to find the direction, I mean the magnitude, but also the direction. So what is the direction for this contribution, of this circuit? Going from here, from D to A, would that be downward, upward, into the page, out of the page?
Would it be
there?
into the page?
Well, it would be out of the page.
Yeah.
You point your thumb in the direction of the current, and your fingers will wrap in the direction of the magnetic field produced by that current. And if you were to do that in such a way that your fingers are, pointing initially toward O, you can see that your fingers will come out of the page in this case. So this is out of the page. Now, on that subject, what do you think about the top arc? Would that be out of the page or into the page?
Into the page, because it's going the opposite direction.
Yeah, so these will subtract each other, not equally though, because one's further away than the other. But there is a longer path length in the top arc altogether. So let's check it out. So from B to C, again, the vectors ds and r are perpendicular to each other. So we don't have to deal with the cross product. It's constant. So we have this relationship, but now, we're integrating, we're integrating from theta to 0. We start here at 0. You can see this from our integration for D to A. So we got to integrate in the opposite direction. So if we want the same limits in the same order, then we have to put a minus sign on the outside. And what I've done here too is I'll replace ds with dr2. I'm sorry, just r2. So ds has been replaced by r2 times d theta. In the same fashion what we did here in the case for the lower arc. And very trivial integration. We now have this, but we have this minus sign to contend with. And of course, R2 is further away. All right, and so substituting in the values for that, we get minus 3.14. Actually, it turns out to be pi, but minus 3.14 times 10 to minus 7 Tesla. So these are two contributions to the magnetic field observed at O, point O. And as someone already pointed out, of course, this is into the page. We have a minus sign that sort of indicates that. So the total magnetic field is the sum of both components. And we'll do that. If you guys see this, you are sharing thing blocking your view of the screen?
No.
No,
I can see the screen.
All we see is the slide.
Okay, well, great. It's just me then. All right, so we just sum the individual components, and that's what we have here. And then by doing so, of course, we get a smaller number, but it's not 0. 0.79 times 10 to the minus 7 Tesla. And how the page positive initially.
I have a quick question. So, I know that you use the right-hand rule to determine the direction, but basically, based on what you just said, can we also just use the the sign that we get after our
Yeah, I mean,
integration?
either way, that's why I did that in that way. We could, in fact, just looked at the magnitude and then say, well, okay, we know, it's from the right-hand rule, and, it must be into the page, for segment B and C. So, yeah, it worked. So, just look out for that. Yeah, I was just trying to be a little more careful in terms of the limits in the integration was all. Is that Jack? Is that right?
Yeah, thank you.
Yeah, sure.
For segment BC, why is it from theta to 0 in the integral?
Oh, because we're integrating. I'm just following the path of the current. So in the lower segment, we're going from side to left hand. Go up, and then now we're going from left hand side to right hand side. So clearly, we're the angle is going in the opposite direction.
Thank you. That makes sense.
Yeah, I mean, like I said, I was telling Jack, it doesn't really matter. It's just you either can take care of the direction based on the right hand rule, or you can do it numerically. Like one, right?
Professor, just a question. Are you gonna post the reference sheets for the exam?
Yeah, later in the week I will do that.
Okay, thank you.
Basically, it'll just be updated from exam 2. All right, sorry, I have to move on here. Now we have a current. Well, it's passing through this long straight wire, radius big R, carries constant current of 40 amps, and it's uniformly distributed across the cross section of the wire. In other words, J current density, is the same everywhere. The radius big R of the wire is 2 centimeters. We want to evaluate the magnetic field of 2 locations, one at 1 centimeter and the other one at 10 from the center of the wire. Okay, so here we want to invoke Ampere's law to solve this. Get the case outside of big R. That's what I'm doing here. So this is basically we're just doing the integration. Path length in this case, and since it's a circular path that we choose with respect to the center of the wire. And they're all each other. So all we need to do is integrate over ds, which is 2 pi little r. Little r is our distance away from the center of the wire, and this must equal to mu naught times the amount of current that's enclosed. And if this is outside, it's the full current. So if little r is bigger than big R, then close. So we now have this for the magnetic field outside the wire. It's a little bit different though inside, and that's will definitely be the case for the distance r equals 1 centimeter. That is less than 2 centimeters. Okay. So only a fraction of the current is enclosed. All right, so we have to continue that. And stated earlier, the current density by stated in the problem. So regardless, what cross-sectional area we choose, J will not change. But yes, of course, the current will change because our cross-sectional area is different, smaller in this case. Just the constant is J. Okay, so this relationship, we're just taking a ratio of the amount of current enclosed, what I'm just referring to, has a smaller cross-sectional area, I prime, divided by I, total amount of current, It's equal to ratio of J times the cross section A prime divided by J. This is this is the full cross section. So this gives us basically the ratio cross section for these two different cases, for being inside the wire and big R total cross the J. So case between enclosed to the final current is this ratio of the radius is squared. Okay, and so again, we invoke Ampere's law. And the amount of current enclosed is no longer I, but is I prime. We want to substitute that for total current, which is this relationship. And so now we have a relationship now between the magnetic field inside. If somehow we're able to measure it, it's not a trivial thing. This is equal to mu naught I times 2 pi big R squared times R. So really, the only thing that happened here in this operation, R squared is now linear in R. Okay, now what we want to do is evaluate these two cases for the magnetic field, get a numerical result out. For the case when we're outside, R at 10 years, so it's related from outside, and so we'll just plug in values for that. 40 amps times mu naught, and the radius, our distance away from the center now is 0.1 meters, and so now we have this relationship here. 8 times 10 to the minus 5 Tesla. Okay, now let's look at the other case. When we're inside wire at 1 centimeter, we have to use this other relationship that we derived. And we now have this, this ratio of radiuses of the big R squared. So we make the substitutions and evaluate this. And it's actually a bigger number, even though we're enclosing less current. It's just that we're much closer to that current than which we're enclosing. That turns out to be 2 times 10 to the minus 4 Tesla. Okay, that's it for that problem. Moving on. All right, so looking at a RL circuit shown here, and suppose the current elements have the following values where the EMF battery that we're using is 12 volts, the resistance is 6 ohms, and inductance is 30 milliamps. What we want to do is find the time constant of the circuit. And we already know this basically, we derived this early on, but I think actually the current, in the reference sheet, this will be given to us. So tau is L over R. So we can then just make the substitution. See, we know what L is, we know what R is. And so that turns out to be 5 milliseconds in this case. Okay, a little more here. Not done yet. Let's say switch 2 is in position A, and then it's basically it's thrown at t equals 0 to s equal 1. S equal 1 is closed. And then we basically determine what is the current at some later time, based on this time constant. Basically, you can think equals close. Now, sometime later, it's given to us as 2 milliseconds. We want to know what the current is. The current would be the same everywhere in this circuit since it's a single loop. All right. So we use this relationship that we derived early on. So it's just the ratio of the EMF divided by the resistance, big R. And basically have values to substitute for this. There's really no manipulation. So you can see basically the I naught is basically 2 amps. And substituting in for time t, which is 2 milliseconds. Tau is 5 milliseconds. They're in the same units here. So we have now this to evaluate, and it turns out to be 0.659 amps after 2 milliseconds. So what would it be when a t is a very big number? Say when t becomes infinite.
It'll just be the maximum current, so epsilon over R.
Yeah, basically it's at 2 amps. You're right. It's just basically epsilon or the EMF divided by R. So that's the maximum. I mean, eventually when the inductor gives up, it says, okay, you win. I'm not resisting anymore. Then at that point, it's 2 amps. All right. Better move on. Sorry. All right, so now let's look at this LC. Okay, so we have a circuit diagram. The battery has an EMF of 12 volts. Inductance is 2.81 millihenries. And the capacitance is 9 picofarads. And the switch has been in position A for a long time. It's just that the capacitor is fully charged. In other words, it's 12 volts across the capacitor. Switch is then on to position B, removing the battery from the circuit and connecting the capacitor directly across the inductor. So the question is, what is the frequency of oscillation for this given circuit when this happens? We know omega is equal to 1 over square root of LC. We want this in terms of frequency. Note, it doesn't say angular frequency, frequency. Omega is equal to 2 pi f. So we have this relationship that we have to contend with. Okay. Plug in the values for that, and it turns out to be 10 to the 6 hertz, 1 megahertz, exactly in this case. So now, what are the maximum values of charge on the capacitor? Part of the question. Well, we know we have this relationship that we have derived before. Of course, I excluded the phase, and it's kind of irrelevant at the point here, but you know, the maximum charge is this amplitude. It's on the capacitor. Qmax is equal to the capacitance times the maximum voltage. And the maximum voltage, of course, as we know, is the EMF 12. This explicitly gives us the charge, maximum charge. 1.8 times 10 to the minus 10 coulombs. Okay. Now, if we want to determine the current, we have to take the derivative of this function for this relationship. And basically, the difference is that in the chain rule, of course, and of course, the cosine is somewhat relevant for this. This is the magnitude of the current that we're interested in. So I max then is equal to the angular frequency times Q max. It's based on this taking its derivative of this function. And omega is equal to 2 pi the frequency. And that's, this is given to us. So we have, this is basically the frequency was given, we calculated earlier. We multiply that times 2 pi. And this is the charge, the maximum charge on the capacitor. And this is the maximum current that we would see in the inductor, you know, during these oscillations. Let's see here. Is anything else? I think that's it for that problem. All right, so let's go on to the next one. Okay. And most doorbells do not have 110 shock to guest, especially most of them are around, you know, it's just less than 12 volts. Most of them are 12 volts. This one is at 6 volts, and it has a current of 0.4 amps. It's connected to a transformer whose primary contains 2,000 turns and is connected to 110 volts, you know, a household outlet. It's typical. So how many turns should that be on secondary to achieve 6 volts? The ratio of the turns, I'm calling in 2 is the 2 is the secondary, the 1s are the primary. So the ratio of the secondary to the primary is equal to the ratio of the voltage secondary to primary. So we have everything we need there. Voltage 610. We have 2,000 turns on the primary. So from this, we can determine what the secondary is. And it turns out to be about 109 turns. Alrighty, part of the problem. The next part is, then what is the current in the primary coil in order to achieve 0.4 amps? So this doorbell is drawing 0.4 amps. So that's on the secondary side. So current in the primary side. So let's make the assumption we have 100% efficiency going from input to output. Also, there's a mutual inductance thing. You could argue with this as well. But the product V and I is the power. So the power going into the input equals the power going to output. And the current in the input is what we don't know. And we know what the output. And so now we the input current, and it turns out to be delivered by the transformer. Well, it's just the product of VI. It could be either the primary or the secondary. Really, ideally, it's the secondary. In the event there was some efficiency factor we want to account for, and so that's what we'll do here. So we'll find out how much power